So if you wanted to solve this distance versus time equation for t, what's your process? F2 group, what'd you do here?
Well, we started with, obviously it was d equals 1/2 at squared, and we started by dividing the 1/2, which is the same as multiplying by the reciprocal, so multiplying by 2.
Multiply by 2, okay.
That gave us 2d equals at squared, and then we divided that by a.
Okay.
So that gave us 2d over a equals t squared.
Got it.
And then we took the square root of both sides, and that gave us t equals the square root of 2d over a.
Square root of both sides. All right. So there's one sort of self-indulgent point that I want to make about this. And this is great, by the way. This is a great choice of steps to get that t isolated by itself. And again, we're working backwards through the order of operations. If there was any addition and subtraction to do, you'd have done that first. There wasn't. So the first thing you did was multiplication and division. Whatever multiplication and division you need to strip everything away from the factor that has a t in it. In other words, get the t squared by itself. And multiply by 2, divide by a. Great. And then finally, after the multiplication and division is done, handle that exponent by taking a root. Again, because we're trying to discover the base of the power t squared. When we want the base, we use a root. If we wanted the exponent, if the thing we were trying to isolate was upstairs in the exponent, we would have used a logarithm instead. But we wanted the base, we wanted t, so we took a root. And the self-indulgent point is this. Let's go forward to part B and finish this point. In part B, what I asked you to do there was to use your rearranged equation, so use your answer, in order to determine how long it will take an object which is accelerating at 9.81 meters per second squared. Meters per second squared. How long will it take that object to cover a distance of 381 meters? So first, the simple question, what information have I given you here? What is 9.81 meters per second squared in this problem?
A.
That's our A. That's our constant uniform acceleration. And the 381 meters? That's our d. Right. So what we were saying before about independent and dependent variables, if I were to plug these two values into d equals 1/2 at squared, I would get an equation that looks something like, what, 381 on the left-hand side equals 9.81 t squared. But that doesn't tell me what t is. That only tells me some equation that t satisfies. And so to find t, we would have to solve that equation for t, right? We would have to do all of these same steps that you did to rearrange the equation to make t the subject. We would have to do those steps. So it's a little unnatural to work with the equation as it's written if we know the distance and we would like to find how much time it takes to travel that distance. The equation that has t as the subject, on the other hand, will not require us to do any algebra to answer this question because we've already done the algebra. All it will require us to do is to plug in these numbers for a and for d. So F2 group, what do you get when you evaluated your answer?
Fully evaluated, t equals 8.813 seconds.
8.813. All right, so I'm going to put in the square root here. And downstairs the acceleration, 9.81 meters per second squared. And you said when you evaluated this, you got 8.83?
8.813.
813, thank you. Seconds. Great. So, 2 points. The second one is my self-indulgent point. Fine. The first one is take a look at the units that are underneath the square root. I kept the units in here, the meters and the meters per second squared. What happens to those units underneath the radical? What happens to the meters?
Well, the meters cancel.
The meters cancel. I have a meters on top, I have a meters in the numerator of the denominator, so a meters on the bottom. Those cancel. What happens to the second squared? It gets cut down to seconds when the square root happens. Right. But where does it end up, numerator or denominator? Because it's in the denominator of the denominator, it ends up upstairs in the numerator. And then when the square root happens, the square root is going to cancel out the square in the second. So indeed, the units of the answer that you got here are the units that we expect if we're looking for a time, right? We're looking for units of seconds. On the other hand, and here's finally my self-indulgent point I'm going to come to. When you take the square root of a number, what do we know about this answer? What is the square root of a number always going to be? If you ask a calculator, let's say. Punch in a square root on a calculator. What kind of a number pops out? Well, is the square root of a number always smaller than the number itself? Try taking the square root of 0.25. Square root of 0.25 is bigger than 0.25.
Right now, you're lying.
Yeah, try it. No, don't believe anything I say. Test it for yourself.
Oh wait, I did 25.
Yeah, you need that decimal point in there. It's kind of important. So whether it's bigger or whether it's smaller, what kinds of numbers are these that pop out of a square root on a calculator? What are they not? Let me put it that way. What will you never see when you compute a square root on a calculator? You're never going to see something negative when you compute a square root on a calculator. But on the other hand, we could get a negative that turns out to be important. So let me rephrase this problem a little bit. So here's a question totally free of any scientific context at all. I just want to know what values of t satisfy the equation t squared equals 25. Right, so if we were doing what we did before, we would just take the square root of both sides, like this. And then on the right-hand side, the square root of 25, if you ask a calculator, pops out to be 5. On the left-hand side, the square root of t squared. Okay. Anyone take issue with this?
It can be -5 too.
It being t. Right. T could be -5. So this is my self-indulgent point. And in fact, it's so self-indulgent that even the authors of this book that we're using seem to have missed it at one point. So what I'd like you to do, how should we have done this problem to avoid missing that negative answer? Well, on the left-hand side, the square root of t squared is not t, it is the absolute value of t. And then on the right-hand side, we still have equals 5. So this is the step that, I would be so happy if every time I saw someone take the square root of a square, they ended up putting in the absolute value. This is a step that if you remember it, you get major bonus points from me.
Got you.
And it will avoid getting an incorrect answer or missing a correct answer, which is worse. So then all we have to do is one more step. How do you solve the equation absolute value of t is equal to 5?
Are you trying to make it just t?
Yeah, we want to get the t by
So
itself.
you can do t equals plus or minus 5.
Exactly. When an absolute value disappears, what replaces it is a alternating plus or minus sign on the other side. So we get two solutions, t equals -5 or t equals +5. So don't forget that little step. This is my self-indulgent point, but I hope that this will help you to avoid what I see over and over again, especially in courses like calculus and even physics, which is a common mistake of forgetting that there are two solutions to almost every square root problem. The only square root problem that does not have two solutions, the square root of 0. Because 0 is its own opposite. But every other square root problem has two solutions.